Hello there, and welcome to the second episode in the Shots in the Quark series about motion. There's no need to have watched the previous episode to learn something from this one, but if you're looking for a deeper, more complete picture of the road from Newtonian mechanics to general relativity, then you can click on the link in the description below to start at the beginning. What we want to know is how we can tell whether an object is really moving, whether it's being acted on by a force or not. In order to do this, Newton introduced the idea of absolute space. Absolute space is made up of an infinite number of fixed points called places, each place serving as a possible location for a material object. True motion, then, was defined as motion relative to these fixed points of absolute space. By Newton's first law, an object not being acted on by any forces would move in a straight line with constant velocity relative to these fixed points. The problem with absolute space, however, is that it's completely unobservable. You can't see or detect the points of absolute space, so how can we tell how things are moving relative to it? A famous consequence of Newton's laws, known as Corollary 5, tells us that there is no difference in the behaviour of a system at rest in absolute space and the behaviour of that same system moving at a constant velocity through absolute space. We'd have no way of knowing if our solar system was at rest in absolute space or moving through it with a constant velocity. The two situations are completely equivalent on Newton's laws. So if we can't detect absolute space, and there's no difference between a system at rest in it and one moving uniformly relative to it, then perhaps we should consider getting rid of the idea altogether. This turns out to be possible. In order for Newton's laws to work, we never needed absolute space at all. All we really need is the concept of an inertial frame of reference. First, what is a frame? A frame of reference is like a particular point of view. I have a frame of reference, you have a frame of reference, everyone has a frame of reference. When you see objects move around you, what you're seeing is how those objects are moving relative to your frame of reference. So if you imagine that you're standing on a train platform and see a train go rushing past at some speed v, then relative to your frame of reference, which we can picture by drawing a little coordinate system, the train looks as if it's moving at a speed v. But relative to the frame of reference of someone on the train, because their frame of reference is moving at the same speed as the train v, the train appears to the person here to be stationary relative to their reference frame. Now, one might worry that talking about systems in terms of these frames of reference may make all motion seem relative. According to the person on the platform, the train is moving. According to the people on the train, however, relative to their reference frame, the train is stationary. This is the situation if we're measuring motion relative to different reference frames. But surely, one would think, there is a matter of fact over whether the train is really moving or not. We're accustomed to thinking that even though the train is at rest relative to the reference frames of the people on the train, that everyone in this situation would agree that the train is really moving. It's this kind of thinking that led Newton to the introduction of absolute space. He and many others at the time believed that there should be a matter of fact over whether an object was really moving. What absolute space is then, is it's just a special reference frame. An object is truly moving if it's moving relative to the reference frame in which the points of absolute space are at rest. We saw, though, that absolute space is a problematic entity. The core of the problem comes from the fact that absolute space is picking out just one special reference frame, when actually it makes no physical difference whether we measure things relative to the frame of absolute space or relative to a different frame, moving at a constant velocity with respect to absolute space. The solution then is not to pick out one ultimate special reference frame, but to allow a whole class of them. Inertial reference frames are the special class of frames. There are plenty of ways of characterising what an inertial frame is, but let's focus on the one directly related to Newton's laws. We define an inertial frame as one in which Newton's first law holds. What this means is that if you're in an inertial frame, you'll see force-free bodies move in straight lines with constant velocity. Now, if Newton's absolute space existed, then the reference frame in which the points of absolute space were at rest would be an inertial frame. This should be clear since, by definition, Newton's first law holds relative to absolute space. So the frame in which absolute space is at rest is clearly one in which Newton's first law holds, and so is an inertial frame. Notice though that this absolute space frame is not the only inertial reference frame. So let's do this. We have our absolute space frame here. So this is absolute space. It's the frame in which the points of absolute space are at rest. Now let's take a new frame, which is moving at some speed u. It's moving in a straight line with a constant speed u relative to the points of absolute space. Now let's take an object. Okay, here's my object, and let's say that relative to absolute space, it's moving with a constant speed v in a straight line. Now notice that if it's moving in the absolute space frame in a straight line with a constant speed, it's also moving in a straight line with a constant speed relative to this new frame. The only difference is that its speed is slightly different. It's going to be v minus u according to this frame. Now, since this object is moving in a straight line with a constant speed in an inertial reference frame where Newton's first law holds, this object must be force-free. What this tells us is that in the second frame, this object is still force-free and it's moving in a straight line with a constant velocity, v minus u. So it's obeying Newton's first law. What this tells us is that Newton's first law doesn't just hold in the absolute space frame, it also holds in this second frame. So this second frame is also an inertial frame. This argument can be repeated for any frame moving in a straight line with a constant speed relative to the absolute space frame. So we don't just have one inertial frame, we have a whole infinite class of them. We see now what the problem with absolute space is. Absolute space picked out just one frame out of this infinite set as being special. But Newton's laws hold in all of these frames, not just one. All these frames are equally special. So we can get rid of absolute space and replace it with this set of inertial reference frames. Remember that one of the key problems with absolute space was that you could never actually know how you were moving relative to its fixed points. There was no difference between being at rest in absolute space and moving uniformly through it. We now see why this is the case. There's no difference between being at rest in an inertial frame and moving uniformly with respect to it. In both cases, you're still in an inertial frame in which Newton's laws hold. In the first case, you're in this inertial frame, and in the second, you're in this inertial frame. So, have inertial frames sorted everything out? Well, there's one more question we can ask. How do you know when you're in an inertial frame? You can never know which inertial frame you're in, but this doesn't matter since they're all equivalent. But it's important to know whether you're in an inertial frame or not. Thankfully though, this is possible. According to Newton's laws, if you're not in an inertial frame, then you'll experience fictitious forces. If you're in a car taking a sharp left turn, you'll feel yourself being thrown to the right. But there's no actual force acting on you. This is a classic example of a fictitious force. You're thrown to the right because your reference frame, the car, is not an inertial one. It's accelerating around a corner. This effect is exactly the same as when you're on a spinning roundabout and feel yourself being pushed out of it. There's no force pushing you out, it's just a consequence of being in a non-inertial reference frame, the spinning roundabout. Since the Earth is rotating, the Earth is a non-inertial reference frame, and so we should see fictitious forces due to the Earth's rotation. And in fact, we do. The Coriolis effect is where wind and other objects travelling long distances over the Earth's surface appear to be deflected. But they're not deflected by any force, it's just a consequence of being in a non-inertial reference frame. To make things clearer, we can expand out Newton's second law in a rotating reference frame. In a normal inertial frame, we just have the usual F equals ma. But in a rotating frame, we can have any of these extra terms. The first is known as the Coriolis force, the second is the centrifugal force, and the third is the Euler force, and these are all fictitious forces. Now, this offers an alternative, possibly more fundamental way of characterising what an inertial frame is. Remember we said before that an inertial frame was one in which Newton's first law held. Well, now we could say that an inertial frame of reference is one in which the laws of physics take their simplest form. In an inertial frame we just have F equals ma, which is far simpler than in a non-inertial frame where we can have something as horrible as this. What all this demonstrates is that we can tell whether we're in an inertial reference frame or not. And that's all that matters when we want to know how objects are really moving. With absolute space, we had to know where the points of absolute space were in order to determine an object's true motion, but this was impossible. With inertial reference frames, all that matters is whether you're in one or not, and this is in principle possible to determine. You're in an inertial reference frame when there are no fictitious forces. By rewriting physics in terms of inertial frames, we can get rid of absolute space, and by thinking about them a bit more, we'll end up very quickly with Einstein's relativity. Thank you very much for watching, and I hope you enjoyed. Please like and subscribe for more Shots in the Quark.